All right, first, a reminder of what we've already thought about. Displacement, that's delta location, uh, is our basic way of quantifying change in location. Delta anything means change in anything, and change in anything always means the final value minus the initial value. So imagine a couple different locations along this line. Uh, Imagine a little bug starting out at the 2 meter mark here on the positive side. So we could represent the initial location with a vector. Uh, the magnitude of the vector, the size of this vector tells us how far it is from the reference point of the coordinate system to the point of interest, and then the sign of this number tells us the direction of the vector. The direction of the vector tells us which way we have to go to get from the reference point to the point that we're interested in. And likewise, a final location of -6. So in that case, displacement, the change in location is just the final value -6 minus the initial value of 2, or -8. Displacement is also a vector, just like position, and the sign tells us the direction of that vector. Negative sign, what that means is that to get from the initial location to the final location, you have to move in the negative direction. And the magnitude, the size, 8 meters, just tells us how far it is from the initial location to the final location. Okay, let's look at a slightly different example. Let's say the bug starts out with the same initial location +2, but then walks over here all the way to the x equals -6 meter mark, and then walks back, ends up at the same place the bug started. At the final location is the same as the initial location. They're both +2 meters. And let's say it takes the bug 60 seconds to do that. Well, we have two different ways of measuring how fast something is moving: speed and velocity. And it's very important to remember that they are different things. As you can see by the symbolism here, velocity is a vector. I've got the arrow symbol on top to indicate that it's a vector. Speed is not. So, among other things, velocity tells you something about the direction of motion, and speed doesn't. Here's our definition of velocity. Actually, the book generally calls this just plain velocity, but strictly speaking, it's an average velocity, sort of an average velocity over this much time. In this case, where the initial location and the final location are both 2, then displacement is final location minus initial location, or 2 minus 2, or 0. So in this particular case, the average velocity was 0. Overall, there was no change in location. At the end of all the movement, the bug was at the same place where it had started. Or to put it another way, there's just as much movement one way as there is movement the other way, so on average, no movement. The average velocity comes out to 0, but the speed does not come out to 0, because speed means something different. Speed we define as just the total distance traveled divided by the amount of time it took to travel that distance. And we're saying it took 60 seconds for the bug to make this round trip. So the total distance traveled is from 2 to -6, that's a distance of 8 meters. And then -6 to 2, that's another 8 meters. So 8 meters one way, 8 meters the other way. That's a total distance traveled of 16 meters divided by 60 seconds. And so the speed is definitely not 0. Speed is 0.027 meters per second. The moral of the story is simply speed and velocity are two different things. They've got different definitions, and therefore they'll give you different pieces of information. Let's think about velocity a little bit more, and let's think about it in the context of a graph of position versus time. Here's position versus time. And just imagine a pretty simple kind of pattern here. A straight line on the position versus time graph. And as I pointed out in the last video, this always means motion with a constant velocity. Now, of course, anytime you have a line, a straight line in a graph, you can find the slope of that line. You do it by just picking 2 points. And let's say this is sort of an initial or earlier time, and a later or final time. You're just thinking about the motion that happened between this time and this time. And at this time, that would have been the location. And at this final time, that would have been the location. And we know the rule for finding the slope of that line. It's just the amount of change in the vertical variable divided by the amount of change in the horizontal variable. Or to write that out algebraically, the slope is just the change in the vertical variable, which is x final minus x initial, divided by the change in the horizontal variable, which is t final minus t initial, which is, well, the numerator looks just like our definition of displacement, and the denominator is just delta t. This means final value minus initial value of time. That's just the time elapsed, the amount of time it took to make this much location change. But we saw this just a second ago. This is our definition of average velocity. So look at the beginning and the end of that series. Slope is velocity, and that's a general principle that you can use all the time, always, whenever you have a graph of position versus time. In a position versus time graph, slope is velocity. Slope is velocity in a position versus time graph. Keep that slogan in mind, and you can do a lot of things. For example, let's look at this graph of position versus time. And that's enough information to tell us something meaningful, probably useful, about velocities and speeds. So let's think of what a velocity versus time graph would look like. And things change at these points, so we'll line them up on the velocity graph because things are probably going to change on the velocity graph as well. Okay, remember the slogan. On a position graph, slope is velocity. So what do we have here? A constant slope, because it's a straight line, and positive slope. Constant positive slope in a position graph means constant positive velocity because slope is velocity. So there's a constant positive velocity. And here, a constant slope because it's a straight line, but a negative slope. So constant negative slope on the position graph means you got a constant negative velocity. And in fact, the magnitudes of these velocities are the same. Right? If this is a velocity of 2 meters per second, this would be a velocity of negative 2 meters per second. Their magnitudes, their absolute values are the same because these two lines are equally steep. If the slope of this line were +2, then the slope of this line would be -2. Because it looks like a certain amount of symmetry here with the angles, you can judge that they're equally steep. Therefore, the magnitude or absolute value of their velocities is the same, even though one is a negative and one is a positive velocity. And then here, again, a constant and positive slope, since that's the slope on a position graph. Constant positive slope means constant positive velocity. Constant positive velocity, but a bigger velocity than before. The slope of this line is bigger than the slope of this line. So this means bigger velocity. The slope of this line is greater than the slope of this line, which means this velocity is greater than this velocity. Of course, you could there are other ways to look at it. There are other ways you should be able to look at it. In addition to the slope is velocity slogan, look at time A. We'll call this time interval A and time interval B, for instance. During time interval A, as time goes by, the location number always becomes more positive, always moving towards more positive values of location, which means any time during time interval A, if you watch for a while, the value of location at the end of your watch will always be bigger than the value of your location at the beginning of your watch, and that means the displacement during all that time, which is just final minus initial, must be positive because this number is always greater than this number, and that means velocity must have been positive because this number was positive, and this number is always positive. This number is positive. This number is always positive, no matter what kind of motion you have. A final time is always greater than an initial time. So what's happening here? That this is always true, which is just another way of saying there's motion always in the positive direction, and in other words, positive velocity is just another way of saying there's always motion in the positive direction. Positive displacement is just another way of saying there's always motion in the positive direction. And then in time interval B, something comparable. Pick any two times within time interval B and compare things at the earlier time to things at the later time, and it'll always be the case that the later or final location is a smaller, less positive number than the initial location, which means the displacement, which is just final minus initial location, must always be negative, and the velocity, since it's just the displacement divided by a positive number, must always be negative. If this is happening all the time, you're always moving towards more negative, less positive values of location, or in other words, you're always moving in the negative direction, as indicated by negative displacements, and as indicated by negative velocity. And the point to hammer home here is that the direction of velocity and the direction of displacement mean the same thing as the direction of motion. Not a really complicated idea, but it is, in spite of being not complicated, it's easy to forget, and you make things more difficult for yourself if you do forget that. Anyway, let's look at one more example of how we can use the slope is velocity idea with a position graph. Here's our position versus time graph. Like that. And then what's velocity like? Let's go that far. Velocity versus time. From 0 to this time, we have a constant and positive slope, which means a constant and positive velocity. From this time all the way to this time, it's the same line, even though it crosses the x equals 0 axis, even though you've got positive locations for part of the time and negative locations for part of the time. It's still one line all the way with one constant slope, and it's a constant negative slope, which means a constant negative velocity. And because this looks like an isosceles triangle, it looks symmetric on both sides, then it looks like the absolute value of this slope is just the same as the value of this slope. Both those lines are equally steep. If this is a slope of 3, then this must be a slope of -3. And then, from this time to this time, you've got one line with one slope, a straight line with a constant slope, and that slope is positive. So constant positive slope on the position graph means constant positive velocity. And it looks like the slope of this line is about the same as the slope of this line. And so if this slope is the same as this slope, that means velocity during this time has to be the same as velocity during this time, because slope is velocity. And then finally, during this last period of time, a straight line, in other words, constant slope, and constant negative slope. Constant negative slope on the position graph means constant negative velocity. And the same magnitude for the velocity as before. So this line looks equally steep as this line, so the absolute value of this slope equals the absolute value of this slope, and all these lines look equally steep whether they've got positive or negative slopes. So this slope is the same as the absolute value of this negative slope because they look equally steep, and it's the same as the absolute value of this negative slope because they look equally steep, and it's the same, the slope of this is the same as the slope of this, so they're all equally steep. In other words, all these velocities have the same magnitude, the same absolute value, the same size, but some of them are positive, some of them are negative. In other words, they have different direction, they correspond to different directions of motion. So that means if you were to take these 4 time intervals here, A, B, C, and D, and B, sorry. is this time here, and then rank them by velocity and then rank them by speed, you get two different rankings. Let's do velocity first. All of these things, all these velocities have the same absolute value, just some of them are positive and some of them are minus. So this might be +3, -3, +3, -3, which means the velocity during time A and time C is exactly the same. And the velocities during time B and D are the same, but they are both negative velocities. So any negative number is less than a positive number. The ranking of speeds looks a little bit different. Remember, speed we think of as just how far you go in how much time, regardless of the directions of motion. So here in time A, we went this far in this much time, and because this line and this line are symmetric, this much time is just the same as this much time, and in this much time you go the same distance, just in the opposite direction. Here you might have gone from 0 to 3 meters in 1 second, and here you went from 3 meters to 0 meters in the next second. So in both cases, the same distance traveled in the same time, same speed. Even though one of them corresponds to a positive velocity and the other one corresponds to a negative velocity. And then C, exactly the same thing. You go this far, say 3 meters in 1 second, 3 meters in 1 second. So you go 3 meters in 1 second or 6 meters in 2 seconds. Either way, you either way, you have a speed of 3 meters per second. It's just that here you had a speed of 3 meters per second moving in the negative direction. Here you have a speed of 3 meters per second moving in the positive direction. So the speed during time C is the same as the speeds we've had before. And here, it's the same thing. Again, you go 3 meters in 1 second, but you go in the negative direction, so it's a velocity of negative 3 meters per second. But the distance traveled is 3, and you travel that distance in 1 second, so the speed is just plain 3 meters per second, same as all the other speeds. To put it one way, speed just measures how steep the slope is without regard to whether it's a positive or negative slope. So if all those lines have the same slope, they all correspond to the same speed. The velocities are different because the sign of the velocity is different because the direction of motion is different. Okay, now you can try some of the same stuff for yourself.